Hi everyone, let us solve this example of power series. Okay, so using some suitable power series, we have to prove this equality. So what will I do? I will start with one power series. So I've started with power series summation x raised to n plus 1 upon n factorial. Okay, so first of all, my target is to find the radius of convergence. Tell me what is Cn here. Cn means multiple of x raised to n or multiple of x raised to n plus 1. So it is 1 upon n factorial. Then obviously Cn plus 1 is 1 upon n plus 1 factorial. Then the radius of convergence will be, so this is formula of radius of convergence. Okay, so now I'm going to put value of Cn plus 1, this value I put, and then I will put the value of Cn, which is 1 upon n factorial. So see here, this n factorial is in denominator of denominator, so it will shift to the numerator and we will have this one. Okay, so do you know what is value of n plus 1 factorial? It is n plus 1 into n factorial. So factorial, that means obviously it will give positive value, so that's why I removed mod. So now that n factorial will get cancelled and we will have, so 1 upon n plus 1. Okay, so as I put n is equal to infinity, 1 upon infinity 0, so that means 1 upon 0 is infinity, so its value is infinity. So that means radius of convergence is infinity. That means this power series which we have considered, this is absolutely convergent everywhere on R. So now I am interested in at which function this series converges. Okay, so for that I will take a sequence of partial sum. So I am considering that Sn of x be the sequence of partial sum. So I have considered Sn be a sequence of partial sum of this series, right? So therefore Sn of x is equal to, first of all I will put n is equal to 0. So you will have x only, since x raised to 0 plus 1 x and 0 factorial means 1. After that I will put n is equal to 1, so you will have x raised to 1 plus 1 2. Getting now, if you put n is equal to 1, x square by 1 factorial, getting, plus x cube by 2 factorial. In this way we can continue and our nth term will be x raised to n plus 1 by n factorial. So after that, to find the limit, I will take limit of both sides as n tends to infinity. But see, you can easily observe that we can take x common here, okay, and you can take outside the limit. So that's why I'm taking x common here. See, if you take x common, so here you will have 1, here you will have x, here you will have x square, and so on. Last term will be x raised to n. See, but as n tends to infinity, so that means this series will continue, n will never terminate. Getting? So you will never have a last term, you will go up to infinity. So this is a series of e raised to x. So that's why we get this is nothing but x e raised to x. That is nothing but sequence of partial sum converges to this x e raised to x. Therefore, our series value of this series is also x e raised to x. See, on the next page I am writing that series converges to this x e raised to x. Now what will I do? I will integrate both sides and I will take term by term integration on an interval 0 comma t. Okay, so already in a problem they have mentioned, right? In a problem they have mentioned by integrating on the interval 0 comma t. So I am going to do the same thing here. See, term by term means what? We can take integration inside this summation. Okay, so I have taken integration on both sides. Okay, so see, 1 upon n factorial is constant. We have to take integration of this x raised to n plus 1 only. So its integration will be x raised to n plus 2 divided by n plus 2 with the limit 0 to t. So here I am going to integrate now. Okay, see what will be its integration. I need to apply u into v formula. Using u into v, we will have, so x as it is, integration of e raised to x minus derivative of x 1, integration of e raised to x, derivative of 1 is 0, so we terminate the process, and 0 to t. So this is the required integration. So now our next task is to put the upper limit and lower limit. Okay, so this is summation n running from 0 to infinity 1 upon n factorial. Let us put t here. You will have t raised to n plus 2 divided by n plus 2. If you put 0, you will have 0, right? If I put t here, t e raised to t minus e raised to t. After that we have to put this 0. 0 into anything 0 and e raised to 0 which is 1. Okay, in the next step I will write. So see, this is summation n running from 0 to infinity. So we get t raised to n plus 2 divided by n factorial and this n plus 2. Here t e raised to t minus e raised to t. E raised to 0 is 1, getting? But see, minus minus plus, so we will have plus 1. Right, so now I'm going to put, okay, what I'm going to put, putting t is equal to 1. Tell me what will you get if I put t is equal to 1? Summation n running from 0 to infinity. If I put 1 raised to anything 1 n factorial n plus 2. Here if I put 1, so 1 e raised to 1 e minus e raised to 1 e plus 1 e minus e will get cancelled. Summation n running from 0 to infinity 1 upon n factorial n plus 2 is equal to 1. These two terms will get cancelled. So let us see what we have to prove. Have we got the same thing which we have to prove? No, a slightly difference. Here 1 we have got and they are expecting 2. But simultaneously there is one difference. Here n running from 1 to infinity and we have taken 0 to infinity. So what will I do? I will put n is equal to 0 first. So if I put n is equal to 0, see what will happen? 0 factorial means 1. Getting, if I put 0 factorial means 1. 0 plus 2, 2. So 1 by 2 plus, now I have to put 1. But now I am taking a separate summation. Getting, that means only 0th term I have made it separate. N plus 2 is equal to 1. So now 1 by 2 I will shift there. Summation n running from 1 to infinity 1 upon n factorial n plus 2 is equal to 1 minus 1 by 2. Here is a plus sign, so if I shifted there, minus n. 1 minus 1 by 2, half. So n running from 1 to infinity 1 upon n factorial n plus 2 is equal to half, and this is a required answer. Thank you.